Greetings and welcome. This is Mr. Waddy. We're taking a look at section 4.6 today called Arithmetic Sequences. And I don't have students with me today. I'm pre-recording this, so I might go a little faster than normal, so you might need to pause more often if you need to. So in this chapter, we've dealt with linear relationships. We've seen points on a coordinate plane. We've been able to draw the line through those points. We've been able to find lines parallel to another line through a point, perpendicular to a line through a point. And then we even ended up working with writing equations of lines when I had a scatter plot, a whole bunch of points that weren't necessarily linear, but if you thought about kind of the average of those points, you could describe their relationship as linear. And so we've dealt with all of these different types of linear relationships, and today we're going to deal with discrete patterns where there's not numbers in between my points, but numbers that are just a list, a sequence, which is actually what we're talking about. So a sequence is an ordered list of numbers. And each number in a sequence is called a term. So here's the first term, here's the second term, here's the third term. I would refer to any particular term with a sub and then whatever position it happens to be in. So a sub 1 in this sequence is 5. A sub 4 would be the fourth term, 1, 2, 3, 4, which would be 20. And then I can talk about, I know this is weird, but it's possible to have a list of numbers in which it is infinite, right? So here it goes on for a while, and then I might refer to the nth term in the list. And sometimes that might be worth kind of recognizing, like, okay, maybe there's a formula to calculate the nth term in a list, and then n could be, right, 4, or n could be 100, or whatever value. And some lists do end up going on forever. So you can have an infinite list. And arithmetic sequences are going to be a particular type of sequence where it's got a constant rate of change. It is growing linearly, although it is still going to be discrete. It won't be continuous. We're talking about only the points that are in the list, not the points in between. So if I was to graph it, it would be a series of points. It wouldn't be a continuous line. So here's an arithmetic sequence. In an arithmetic sequence, the difference between each pair of consecutive, that means side-by-side terms, is the same. All right, so we might call this a constant rate of change, right? If I was thinking in terms of ordered pairs earlier, right? So every new term in my list is the same distance apart, right, from the one before it as every other. So there's a common rate of change, a constant rate of change, and we'll call this the common difference. All right, this number that is the difference between any consecutive or side-by-side points in my list. Each term is found by adding the common difference to the previous term. All right, so arithmetic sequences are a type of linear relationship, right? A discrete linear relationship. And so we're not necessarily going to be dealing with too many graphs of them, but we might be dealing with them as, right, they've been suggested, a list. And so here's a classic problem that says, write the next 3 terms of the arithmetic sequence. So I've got to figure out, first of all, what is that common difference? How can I find out what I am growing by constantly each time? Because I actually have to make sure that this is arithmetic. I have to make sure that there is a common difference between these points in order for my detection of a pattern and application of that pattern to even work. So to go from -7 to -14, it's getting smaller, and it's getting smaller by 7. So it's decreasing by 7. To go from -14 to -21, it's getting more negative. It's decreasing by 7. -21 to -28, it's decreasing by 7. To calculate your common difference, what you can do is take any term and subtract the term before it. So if my term was a sub n, then the term before it would be 1 less than that, right? If my term is the second term, the term before it is the first term. If my term was the fourth term, my term before it is the third term, one less term. So if my term that I'm describing is a sub n, the term before a sub n would be a sub n minus 1. Notice this minus 1 is on the level of this subscript. I'm referring to the term before it. And any two consecutive terms will work. So if I wanted to find the common difference, I could have done negative 21 minus negative 14, right? Any two consecutive terms I can pick and kind of plug in this formula, and it will give me the common difference. So I've got negative 21 plus, because the double negative, 14. Their signs are different, so I subtract the numbers. I would have gotten 7 and take the sign of the more influential. So notice whether I'm recognizing it from the list or using a formula, I can find this common difference. This common difference is somewhat like our slope. All right, that's why I'm kind of writing it in green. I figure it might be helpful. So it's somewhat like our slope. Now, if I want to find the next term in the list, all I've got to do is keep moving by the common difference. So I would subtract 7 from 28, and I would get negative 35 is the next number in the list. I guess it would fit right there. Maybe I'll just turn this into an underline, blank, blank, blank. So negative 35, subtract 7 from that, it's going to be negative 42. Subtract 7 from that, it's going to be negative 49. So I'm able to find the next three terms in the list by continuing this arithmetic sequence, continuing the pattern, using the common difference to find each new number. So it's pretty easy finding new numbers in our list if we just simply keep adding to them. Let me tell you what, we'll do some quick arithmetic sequence examples here. We'll even practice with some, you got it, decimals and fractions. So it says, write the next three terms of the arithmetic sequence. So let's first of all find the common difference. So if I find the common difference between, say, these two, if I want to just avoid the negative, I would have done 12 minus 0, and I get 12. Actually, I'll write it this way. D equals 12. So this is a positive common difference. So the next terms in my list are going to be 24 plus 12 is 36. The 36 plus 12 is going to be 48. And 48 plus 12 is going to be 60. And so these are the next three terms in the list. Let's find the common difference for this one. So any two consecutive terms work. I think these ones will be the easiest ones to work with, but any two side-by-side terms will work just fine. So D is equal to 1.4 minus 1 is just going to be 0.4. It's positive. It is increasing by 0.4 for every term. So 1.4 plus 1 to get the next term is 1.8. 1.8 plus 1 is going to be 2.2. 2.2 plus 0.4 will be 2.6. And so I complete, or I find the next three terms. I guess this list could go on forever. It kind of is implied by the ellipsis there. I can find the next three terms by just continually adding 0.4. Oh dear, look at this one. Oh dear, dear, dear. Guys, are you scared yet? I'm scared of this one. So my common difference I could find by subtracting any two consecutive terms. Now notice this one's getting smaller. Maybe this one's I think is actually easier to look at this way. To go from 4 to 3 3/4, or 3.75, I'm subtracting a quarter. All right. I also could have done this by doing 3 3/4 minus 4. And yeah, I don't do math that way. I would convert this to a improper fraction. 4 times 3 is 12, plus 3 is 15/4. Okay, 4 times 3 is 12, plus 3 is 15. It's still over fourths. And 4, if I want to write that in terms of fourths, it's currently over 1, but I can't subtract unless it has a common denominator. So I'd have to multiply by 4 over 4. Because multiplying the denominator by 4 will give me the same denominator. And I can't just multiply the denominator. I have to multiply the top because this is now equivalent to multiplying by 1, right? And multiplying by 1 does not change the value. I'm just changing the way this looks. It's like you're the same person even when you're wearing a Halloween costume. So negative 4 times 4 is going to be negative 16. Or, okay, I've already got the minus sign there. So 16 and 4 times 4 is that. So 15 sixteenths minus 16, 15 fourths minus 16 fourths will be negative 1/4. So that is the value of D. Now, in this case, like I said, I think it was easier to just recognize doing that. But the formula would have worked. So 3 1/4, if I subtract a quarter, would be 3. 3 minus a quarter would be 2 3/4. 2 3/4 subtract a quarter will be 2 2/4. But that's the same as, like we did up here, a half. 2/4 reduces to a half. So there are my answers. So that's not that bad, right? That's not that bad. What if I wanted to graph these, though? What if I wanted to kind of visually look at how this is changing? And that's what we're going to do in example 2. And the way we could think about it is we're actually going to make a list of ordered pairs. So we're going to think about which term am I at. So that's going to be my nth axis, n term axis. And what is the value of that term? So here's what's the position, what's the value of the term. So the position of my terms are 1, 2, 3, 4, and it keeps going on. And the values of my terms, the a sub n, right? The a sub 1 would have been 4, the first term. A sub 2 would have been 8, the second term, right? And then 12 and 16. So I'm going to have my n-axis here, and I'm going to have my y-axis is going to represent a sub n. And so let's plot these points. And just like we plotted before, so over 1, up 4. Oh dear, wait, I've got to go at least up to 16. I'm going to run out of space. Maybe I should change my scale. Let me count by 2s, perhaps. So 2, 4, 6, 8, 10, 12, 14, 16, 18. There we go. All right. My n-axis, I think I'll be able to count by 1s just fine. So over 1, up 4. There we go. Over 2, up 8. Over 3, up 12. Yep, right. So the third term was 12. The third term is 12. And the fourth term was 16. So right there. So here are my points. Let me just make those a little bit bigger for you guys. And I know I'd be super tempted to connect these dots, but remember, this is a list. Like, there's not like a 1.5 term. There's just like the first term and then the second term. There's nothing in between this list. This is a discrete list. And what do we notice? We notice that these points, they have a linear relationship that you could perhaps predict the next location by doing up, I guess in this case, yeah, it's up 4 over 1, up 4 over 1, up 4 over 1. I realize that these are 2 squares, but remember my squares each count as 2 for the vertical axis, right? So up 4 over 1, up 4 over 1. And I could predict the location of other points. So it's a linear relationship, right? These points lie on a line, okay? The points lie on a line. So let's see, what about this kind of problem, example 3? Can we identify an arithmetic sequence, whether or not this is arithmetic, by looking at the graph? So here's a graph that's given to us, and the question is this arithmetic? All right, well, it's discrete because they're not connected. One of the ways we could do this is turn this into a table now, right? So I could have my n and my a sub n. Actually, I'll do it this way. And so I'll have my first term was 15, my second term was 12, my third term was 9, my fourth term was 6. And so is this arithmetic? Well, what I would have to test is there a common difference? Is this decreasing by the same amount? So notice this is reducing by 3. This is reducing by 3. 9 minus 3 is 6. So this appears to be arithmetic. There is a common difference, so it is arithmetic. Notice that graphically speaking, it's going down 3 over 1. There's our point. Down 3 over 1. There's a point. Down 3 and over 1. It's hitting a point each time, so there is a common difference between our points. So that's my answer. Since there is a common difference, which is 3, all right, d equals 3, it is an arithmetic sequence. Right? Good. So, and I'm sure you could see that we could continue the pattern graphically or in list form and be able to generate more points. Let's see. Now, what if I wanted to find out what a later term in my list was? What if I wanted to find out what a later term in my list was without having to just do one at a time counting? Because what if I asked for like the 100th term in a list? I wouldn't want to have to do that all 100 times in order to figure it out. So let me generate this table for us. All right, something like this. And so my first term in my list we refer to as a sub 1. Okay. My second term in my list would have been a sub 2, but I want to write it in terms of a sub 1 and d, my common difference. So my second term would be a sub 1, and how do I get my common difference? Well, I would have added d to it, right? So added d to it, my common difference. So a1 plus d is the same as a sub 2. Right? Over here, 4, right? If I have like 4 plus 3, I would have gotten 7. So my second term would be 7, but I'd have some common difference, right, that I'm calculating. Now, if I wanted to find the third term, I would do 7 plus 3, right? 7 plus 3. But let's write this in terms of 4s, okay? So 7 plus 3, where did 7 plus 3 come from? Well, that came from the 4 plus 3. Is where that 7 came from. And so let me replace 7 with 4 plus 3. So there's 7 plus 3, right? So 7 plus 3 would give me my next term. But instead of doing 4 plus 3 plus 3, and then maybe you'd realize for the next term it would be 4 plus 3 plus 3 plus 3, repeated addition, we have another way of describing that. Use multiplication. Right? Adding 3 twice is the same as just saying 4 plus 2 times 3. And 2 times 3 is 6, plus the 4 is the 10. Here, so that would have been my third term. Let's see, make sure I don't run out of space here. So for the fourth term, I would have done 4, and I would have added 3, then added 3, then added 3, and I added a total of 3 3s. So that's 9 plus 4, which is 13. And notice 7 plus 3 is 10, 10 plus 3 is 13. That this does appear to be continuing as a pattern. All right? And what would my nth term in this list be? Well, I would have taken 4, I would have added some number of 3s to it, right? Added some number of 3s to it. And the question is, what number of 3s gets added? What number of 3s gets added if I'm finding the nth term? Well, when I was finding the fourth term, I added 3 3s. When I was finding the third term, I added 2 3s. When I was finding the second term, I added 1 3. So it appears as though the number of 3's I add is always 1 less than the number of the term. So for the nth term, the number of 3's I'm adding is 1 less than n minus 1. Let's write this in terms of this. So this one's always going to be a sub 1, a sub 1, a sub 1. And I'm adding some number of d's. So for the third term, I would have added 2 d's, 2 of the common difference, right? 2 times the common difference. For the fourth term, I would have added 3 times the common difference. And for the nth term, I would have added n minus 1 times d. All right, let's see. N minus 1 times d. Right, I add 1 less than the term multiplied by the common difference. And that's how I could generate a formula for the nth term in a list. Now, why is that formula beneficial? Well, like I was saying, if I wanted to find out the 100th term in a list or the 1000th term in a list, I wouldn't want to have to sit there and do the work over and over and over. And I know I showed you guys how to use spreadsheets earlier. You could technically train a spreadsheet to do it pretty quick, but why not use a formula? So the nth term in a list is equal to the first term plus n minus 1, where n is the number of the term I'm looking for, times the common difference. And so this is a formula. It's a linear formula. And we're going to be able to use it to find new terms in our list that are farther down the line. Okay, so here we go. Let's label what we got. I'm actually going to call a sub 1, I'm going to label in red. D, I was labeling in green. That was like my slope. A sub 1 is my first term. That's my starting value. So I'm kind of imagining that to be like my y-intercept. And then my nth term is my output, sort of thing like that, and n there as well. So what I'm going to do, actually, should I just commit to a color for n? Maybe I should. Maybe I should. Yeah, let's make n equal to orange, and yeah, that'll be good. So write the equation for the nth term of the arithmetic sequence. Blah, 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 blah. All right. So what do I know? I'm looking for a sub 50, so that means n equals 50. I know the first term in this list is 14, so a sub 1 equals 14. So the first thing I want you to do is actually go through and label all of these things, all right? Let's see, how can I find the common difference? Well, it's not one of these numbers. The common difference can be found by figuring out what was being added or subtracted each time. In this case, it's subtracting 3 each time. You also can find the common difference by subtracting any 2 consecutive terms, but here d equals negative 3. So if I want to find a sub 50, a sub 50 is going to equal, now this doesn't mean 50 times a, all right, this is like the name of a single term, okay? So I'm not at no point am I going to try to divide both sides by 50. This is my variable name. So a sub 50 is going to equal a sub 1, so that's 14, plus n minus 1, so 50 minus 1 times d, which is negative 3. Careful, careful, careful with this parentheses here, because d is negative, this is multiplication. If I don't put these parentheses, it will look like I'm subtracting 3. That's not what we're doing. We're multiplying by negative 3. So I labeled everything, I plugged it into the formula, and now I'm going to just simply evaluate it. Okay, so let's see. So that's 14. I'm just going to PEMDAS this. That's going to be 49 times negative 3. All right, you might reach for a calculator here. 49 times 3 is going to be negative, so it's subtracted. But actually, check this out. 3 times 50 would have been 150, and it's 1 less number of 3's than that. So what's 3 smaller than 150? That should be 147. In this case, actually doing this subtraction won't necessarily always be the most beneficial. You could have actually thought of this as distribution. 3 times 50 would have been negative 50, and 3 times 1, all right, negative 3 times negative 1 would have been plus 3. And when I combine those, I would have gotten 147 negative. All right, so sometimes it might be easier to do distribution than it would be to do the subtraction first. And that's a distribution is a time in which you can kind of override PEMDAS when you do so carefully. So let's see, 14 minus 147, their signs are different, so I'd subtract them. 147 minus 14 would have been 133, and I would take the sign of the more influential. So the 50th term in this list is negative 133. And that's way better than having just sat there, minus 3, minus 3, minus 3, minus 3, minus 3, minus 3, and then, oh wait, I think I lost count. How many minus 3s did I do? And not remembering which term you were on, right? So let's do a couple other examples here of this, because this is using a formula, right? This is a little bit tricky. I want to make sure we get this right. So let's see. So here's problem 8 from the monitoring progress is technically what it is. Let's see. So let's say what am I looking for? 25. So n equals 25. I'm looking for the 25th term. My starting value, my first term, a sub 1 is equal to 4. My common difference, d, is, let's see, oh, that's an easy one. Looks like plus 1, so it's positive 1. And so if I want to find the 25th term, a sub 25 is what we refer to that as. I'm going to do 4 plus n minus 1 multiplied by d. And so I'll have 4 plus 25 minus 1 is 24 times 1. That's just 4 plus 24. That's 28. And so the 25th term in this list is 28. No es más mal, right? Not that bad. Here, let's do un otro problema. Maybe we'll just do just this one more for sake of time. All right, so what term am I looking for again? The 25th term. So that means n equals 25. My first term, a sub 1, is 8. And my common difference, which I could find by subtracting any 2 consecutive terms. Actually, let's do that in this case. How would I get from 24 to 32? Well, I can do 32 minus 24. Those aren't the friendliest numbers in the list. I could have found that the common difference is 6 and then 2 is 8. All right, so here's my values. Label these for me, okay? Like mandatory, label them. A sub 25, according to the formula, is my starting value plus, weird plus sign there, plus n minus 1, so that's 25 minus 1, times my common difference. Okay? Times the common difference. Yeah, that's actually, in this case, we happen to have a starting value of 8, and it was being added by 8, so that's why those 2 8s are showing up. So let's see, that is the same as 8 plus, and I think I might use distribution here, just to show you that you can. 8 times 25, well, 4 times 25 is 100, so 8 times 25 must be 200, and 8 times negative 1 is minus 8. Oh, actually, look at this. 8 minus 8, those cancel out. This is just 200. So a sub 25 is equal to 200. No es más mal. Not that bad, right? Not that bad. Let's see. Let's do one last problem. One last problem. Example 5. How am I doing for time? Ooh, yeah, this video is a little bit long. That's okay. All right, online bidding for a purse increases by $5 for each bid after the $60 initial bid. Write a function that represents the arithmetic sequence. Okay, so in this case, I'm going to leave, I'm going to write an equation for a sub n and leave it in terms, all right, of n. So n equals n for us, all right? My starting term, a sub 1, is $60, right? My common difference, they told us, is 5, but I also could see that it's increasing by 5s here. This is arithmetic, so the common difference is 5. And so when I write my function, right, I could say that a sub n, let's see, ooh, they're sneaky. Yeah, I'll write it this way first, would have been 60 plus n minus 1, so this is still in terms of n, multiplied by 5. Now they wanted it in function notation, so we'll write this as f of n. We'll just replace a sub n with function notation. Equals 60 plus n minus 1 times 5. So let's simplify this a little bit. Distribute, that's 60 plus 5n minus 5. Combine like terms. So f sub n is equal to, and I'll put the variable first, I like that, 5n, and 60 minus 5 is plus 55. And so here is a function, right, for the nth term in the list. Okay, all right, here we go. Ooh, it's getting interesting here. Now they're asking us to graph the function and then answer the question regarding what number bid was the winner. Actually, let's see. So, graph the function. Graph the function. Here we go. So, I can plot the points that I had, right? Okay, so let's see. So, n is the number of the bid. Those are increasing by 1s. My lowest number was 60, and then was increasing by 5. So I think I'm going to put a jog in this graph. I'll start at 60, and then 65, 70, 75, 80, 85, 90, 95, 100, right? 105, 110. Okay, so there's the value of the bid. If I want to graph this, I'm going to plot these points. We had the first bid was at 60, right? 1 comma 60, right? Let me just scroll up so you can verify that. I don't want you to think I'm just, right? So the first bid was 60, second bid, third bid, fourth bid. So I'm just plotting these points, just like we did earlier. Another way I could do it is go up 5 over 1, all right? Up 5 over 1. 5, of course, in this case is 1 grid unit high. Up 5 over 1. So here's my point. So like here's like 4 comma 75. All right, 1, 2, 3, 4, and 75. Right, so there's my points. Now it asks the question, the winning bid is 105. How many bids were there? How many bids were there? Now, I could maybe continue this pattern, up 5 over 1, 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 and I could predict that point and then try to figure out, okay, what number bid was that and count it down here, okay? But I also have a function, and basically what they've said is the winning bid was 105, so that's f of some unknown n is 105, okay? So let's plug 105 into this function. Here, I'll even write that down. Substitute right in here. Beep, 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 beep. For the entire thing. I'm not plugging it in for n, I'm plugging it in for the output. So I'm going to have 105 equals 5n plus 55. So let's solve for n, and that's going to answer this question. So I'll subtract 55 from both sides. La 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 la. So that's going to be 50 equals 5n. Oh, definitely divide by 5. That's how you undo multiplication, right? by 5. You divide by 5. And I'll flip it, n equals 10. So that means the 10th bid. There were 10 bids. All right, very good. And is that what I would have predicted here if I followed this down? 2, 4, 6, 8, 10. Voila. So that would have been 10, 105. And so the pattern continued. I could apply the pattern. Theoretically, you could have fake drew a line, but obviously this is not a linear, it's a linear pattern. It's got a constant rate of change, but the points in between don't count. Only the points that are on actual n values, actual terms. All right, well, thanks for watching, internet friends. Hope you guys all have a marvelous day. Bye-bye.